Hey guys, so we are going to continue our lesson on intermolecular forces, and we are going to focus on the three types of intermolecular forces and the effects they have on the properties of compounds. Okay, so these are guided notes. So for molecular solids, I would prefer to talk about the type of intermolecular force and then talk about how to recognize it. Okay, so the molecular solids, these are all intermolecular forces. I'm just going to write IMFs, but the three types of IMFs are listed here, here, and here. Okay, so for the IMFs, the first one is hydrogen bonding. Bonding is in quotes on your paper because it's not a true bond. So this is what you need to know is it is the strongest attractive force. So the strongest attractive force, and I'll also want you to write down that it is not a true bond. I do not want you to think that it is a bond, but it was the strongest attractive force that was once thought of as an actual bond. Then, as technology advanced, scientists realized it was not. Okay, so to recognize this, you're going to have hydrogen bonded to one of three things. It can be bonded to nitrogen, oxygen, or fluorine. And I want you to look at the periodic table over here on the wall. Now, you in the video, you're not going to see this, but if you were looking at a periodic table, I want you to notice all three of those are all lined up together. They're all on one row. So those three, are all going to be your dead giveaway that it is a hydrogen bonded molecular force, intermolecular force. And some examples would be, okay, so write these three examples down. So for oxygen bonded to hydrogen, your example is water. Water actually has super unique properties. This one has the most hydrogen bonding. Okay, so water is one example. The example with nitrogen is NH3. And then the example with fluorine is HF. Okay, so it has to be hydrogen bound to oxygen, has to be nitrogen bound to the hydrogen, or fluorine bound to the hydrogen. Okay? The next set of examples, these are all given, but we need to talk about dipole-dipole forces. So I'm going to switch to a different color, and that way they don't run together. And let's talk about that. So for this next type, I need you guys just to know, instead of it being the strongest, it's in the middle. So it's the intermediate. So it is our intermediate attractive force, meaning it's not quite as strong as hydrogen bonding. It's kind of right there in the middle. And these are seen in polar covalent bonds. I do not know why when I'm writing this wants to glitch. Polar covalent bonds. Okay. So if we had more time, if coronavirus didn't happen and we weren't on a hybrid schedule and all that crazy stuff, we would have time to get into the structures that y'all just learned how to draw and how to determine if something is a polar covalent or nonpolar covalent or a nonpolar covalent bond. So anytime that you have those electrons that are left on the central atom, I want to draw water really quickly for you. So anyway. So remember whenever we had drawn water, and water had 2 electrons here and 2 electrons there, and there's electrons left on the central atom? I want you to notice that is a really polar bond. It's also a really polar molecule because you have electrons that are left over. on your periodic table, you also have electronegativity values. And if the difference in electronegativity is a certain number, then it's going to create an individual bond that is really polar. Okay? Well, fortunately for y'all, we're not going to have time to get into all of that. Okay? But we're going to look at trends in boiling points, melting points, and we're going to be able to make predictions on what the type of attractive force is that's going on. But I wanted you to see an example of what a polar covalent bond looks like, and then a polar molecule. So that's dipole-dipole. You see that in dipole-dipole is also seen in things that hydrogen bond, but the dominant force that's present is always the stronger one. Okay? So with water, we don't think of dipole-dipole forces, we think of hydrogen bonding. I want you to notice that you have HF here also, but there's also carbon. Okay, so this makes it not exclusively hydrogen bonding because you also have some carbons in there that sort of get in the way. All right, let's move on to letter C. I want you to notice something about the compounds in letter C, and this is the dispersion forces. In letter C, there are things like this one, which is C6H6, which it's got a common name, which is benzene. Notice that you only have carbons and hydrogens. For the other molecules, notice that you have two of the same molecule bound together. If you have one molecule that maybe has a tendency to draw electrons to it, or maybe not hold electrons as closely, okay, then if there's two of the same kind, they're going to share the valence electrons equally. So if you have an equal sharing of electrons, you have a non-polar covalent compound. Okay, I know y'all are freezing in here. So for a non-polar covalent compound, you have dispersion forces. So I want to mention, these are all non-polar covalent. So you need to look for those. And it's always going to involve either carbon and hydrogen in whatever numbers, or elements that are that element bound to itself. And what you need to know over here about the description, these are the weakest IMFs. Remember, IMFs is just intermolecular forces. I just don't want to write attractive force again. And these can be quite strong in very large molecules. So just know that there's a continuum in the type of attractive force, and there might be some overlap. So for instance, the dipole-dipole forces, I'd already told you that's medium strength, but if you have something that is only dispersion forces, and the dispersion force involves a really large molecule, well then that attractive force, even though it's not as strong as a dipole-dipole force, that one particular example may be a stronger attraction between those molecules than something that only has dipole-dipole because it's a very large molecule. Okay, so just know, just like with solids, liquids, gases, we teach that there's like different states of matter, but there are some things that are in that continuum that kind of overlap. Like there's like a gel, which is like a solid liquid. You know what I mean? Slime, stuff like that. So same thing with these attractive forces. We're going to categorize things, but just know, just because like one thing is maybe in the middle, it may be kind of, these might be really similar in strength, but we're not going to have any kind of questions on the next test that have to do with something that's like super close. Okay? Finally, the atomic solids, these are a special case of the dispersion forces. Some examples would be if you have any of the noble gases. So I want us to write these examples here. So we have helium, neon, we're just going to write out all the noble gases, argon, krypton, xenon, radon. They all have dispersion forces, okay, and we're not going to write anything else there. So the next thing we're going to do is move on in the practice, and we're going to categorize. Okay, so now we are going to talk about how those physical properties are affected. So we're going to fill in some blanks. So we're going to talk about the strength of the forces and how they affect melting point, boiling point, and some of these other properties. So your first blank is stronger. So we're going to think about the stronger the forces, the effect they'll have on these different things. So if you have a strong attraction between, let's say, water molecules, that strong attraction is going to affect the melting point of that substance. So water going from a solid to a liquid, that's melting. Think about if the attraction was even greater. And you're going from a solid to a liquid. Are you making the molecules get further apart or closer together? Y'all tell me. So going from a solid to a liquid, are the particles getting further apart or closer together? They're getting further apart. So if they really want to stay attracted, is it going to require more or less energy to break them apart? More. So it's going to make the melting point higher. So the stronger the forces, the higher the melting point. I'm going to go to another color just so these don't all run together. What about boiling point? You're going from a liquid to a gas. It's also going to be higher because you're spreading it out even more. Okay, make sure you're writing this down. So the stronger the forces, higher the melting point, the higher the boiling point. Vapor pressure is another one. So like these three I want y'all to focus on the most. Vapor pressure, don't read that technical definition. That just means you have particles that at the surface want to go ahead and turn into a gas. So it's kind of like rubbing alcohol. If we were to set it out on the counter, it would vaporize all by itself. You don't have to add any heat to it. That's turning it into a gas. Would it do that as easily or not as easily if the particles want to stay attracted to each other? No. So it's going to make the vapor pressure lower. Okay? And then these last two, I'm going to change the color on. We're going to talk about it, but I won't test you on this. Viscosity is basically the, let me make sure that I'm consistent here. Viscosity is a liquid being kind of like thick and syrupy. So let me write this in here, and then we will talk about the trend or the pattern effect. So if something is thick and syrupy, okay, I don't know if that's a real word, but we're going to make it a word. Would it become more thicker and syrupier if the attractions were stronger, or would it be less? It'd be more because they want to stay together. So the higher the viscosity, okay, and that viscosity, I don't know if y'all have had to change oil in automotives, but the thickness of the oil is called the viscosity, and the more attractions there are, the more viscous the oil is. So, I have no idea. In automotives?
No.
Biology? Huh, interesting. And then surface tension, that's whenever you take drops of water and you can put it on a penny. So the more you put on a penny, the more it bubbles up. They're staying together. So would you notice stronger attractive forces making more, like a higher surface tension or a lower surface tension? Higher, okay? All right, again, the only three that I really want y'all to remember for a future test is A, B, and C. Okay, so we're going to do one of these examples, and then I'm going to run out of time on the video, and we'll do the rest without the video. So the types of intermolecular forces that it would occur in each. So for letter A, everything is going to have dispersion forces. So we can either have hydrogen bonding, we can have dispersion, excuse me, let me go in order, hydrogen bonding, dipole-dipole, or dispersion forces. Well, everything is going to have dispersion forces. Do we have a dipole-dipole in letter A? Do you have things that are polar covalent? Yes, we do. Okay. Letter B. you have